As we move through 2026 and look ahead to the future of energy, the grid currently faces three key mismatches: time, location, and demand. In this timeline of solar production across a typical day, output rises quickly in the morning, peaks in the afternoon, and falls again when the sun sets. But electricity demand often peaks in the morning and evening, when people are waking up and returning home from work. It means the grid can have too much power in the middle of the day here and not enough on the shoulder windows on the early and late side. So that's time, and the second mismatch is location. You see, power used to be generated close to the places that needed it. Today, much more electricity, though, is being built where the solar and wind resources are the strongest, places like West Texas or the deserts of the Southwest. It's even a global trend, like in Chile, where energy is produced in the north and must travel hundreds of miles down the coast south. And over in Ireland, offshore wind farms generate electricity far from the cities that rely on it. That power now has to travel further and further and shares transmission capacity with the rest of the grid, turning these lines into something of an energy freeway at rush hour. And building new transmission is slow, taking decades to plan, permit, and construct. The final mismatch we'll talk about is demand. This chart shows global electricity use tied to the internet economy, from traditional data centers to networking and transmission. For years, the growth was steady, as you'll see in green. But AI training and querying here in blue will drive a sharp jump up in electricity demand over the next decade. And it's not just the amount of energy either, it's the speed and magnitude of the energy swings that are now challenging all upstream and downstream participants. AI workloads often run in large bursts during model training, shown in this chart, creating several spikes in just seconds rather than a smooth, predictable usage. And that variability makes balancing the grid much harder as more data centers come online. Now, with all these mismatches facing the grid, let's go back and show how batteries can bring stability to each part of the system. Starting with demand, batteries allow large electricity users like data centers to store energy and deliver it in milliseconds when spikes occur. So rather than running power at a constant level up here in red to cover those spikes, the steady state can remain lower in yellow, while batteries provide the responsiveness here in green, helping large loads pull less from the grid. Moving up, they also help solve the mismatch of location by storing electricity all along that proverbial highway and releasing it when transmission becomes available, essentially adding electron on-ramps with stoplights along this whole path, optimizing flow and eliminating those traffic jams. Finally, at the top, batteries can help solve the mismatch of time by capturing excess solar energy produced in the middle of the day here and delivering it during those shoulder hours when demand rises and solar production disappears, reducing the need to start up the more expensive gas peaker plants to meet that ramp. Across all these mismatches, battery systems are becoming a critical piece of modern energy infrastructure, giving utilities, companies, and communities more control over how electricity moves without waiting for a new grid. FlexGen helps companies turn batteries on with their supply chain management, integration, and commissioning teams, and then keeps those batteries on for 15 plus years with proactive monitoring and its cutting-edge energy management software, Hybrid OS. Learn more about how intelligent software orchestrates these grids and data center assets at flexgen.com.